In this video, we're going to take a look at factoring by difference of two squares. So let's first list out numbers that are our perfect squares. So things like 1 squared equals 1. So let's write 1 squared is 1. 2 squared equals 4. 3 squared equals 9. 4 squared equals 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. And 13 squared is 169. And we can certainly keep going, but I think within that list, you'll have most of what you need. And we can use our calculator if we need anything else. So difference of two squares factoring is different than the other types of factoring because it just follows a pattern. You check to see if you have a difference of two squares when you have a binomial that's left over or you're given a binomial, and you notice that your terms are both perfect squares. That means that the coefficient can have an even square root, and the variables have an exponent that evenly divides by 2. And then difference of two squares is very important because this type of factoring only works when two perfect squares are being subtracted. And you factor that into their square roots with a plus or minus for, like, you have one of each sign, a plus and a minus. So let's take a look at some examples to show you what this is talking about. So x squared minus 1. We notice we have a perfect square variable because the 2 is divisible by 2 in the exponent. And then 1, if we were to take the square root of it, it comes out evenly as 1. So the square root of x squared is x, and the square root of 1 is 1. So following our pattern for difference of squares, we would write x plus 1 and x minus 1. Now for this first example, I'm just going to show you why it works to have a difference of squares. So if I FOIL this back together again, I would get first times first gives me x squared. Outside times outside gives me negative 1x. Inside times inside gives me 1x. And then last times last gives me negative 1. But notice the two terms in the middle here are going to cancel each other out because you have a negative and a positive 1x, and they will cancel out or add up to 0. And then you end up with x squared minus 1, which in factoring, we always want to be able to multiply back together and get what we started with. Now, it would not work the same as if we had x plus 1 and x plus 1, because that would be x squared plus 1x plus 1x plus 1, and the 2 in the middle would not cancel out. And for the same reason, if they were both a negative, they would also not cancel out. So it doesn't work any other way except for the pattern that we use for difference of squares. So there's always their square roots, and there's always a plus and a minus for our factors. So let's look at another one to get used to this pattern for a little bit. So r squared minus 100. We notice we have a perfect square variable because the exponent is evenly divisible by 2. And then we can tell that 100 is a perfect square. And so it comes out evenly when we take the square root as just 10. So we would just factor that into r plus 10 and r minus 10. And you can write it as r minus 10 first and r plus 10 second. It doesn't matter which order. You just need one of each sign. All right, so let's look at z squared minus 36. So we notice those are perfect squares and there's a minus sign. So take the square root of each one and put z plus 6 and z minus 6. And it's as simple as that. So once you get used to this method, it does work pretty quick. So p squared minus 121. They're both perfect squares. So we factor that into p plus the square root of 121. And use your calculator if you need it, or use our notes at the top of the page, because I noticed I did write that right there. So 11 squared I can tell is 121. So p plus 11 and p minus 11 would be the factors. All right, so let's just do a couple more down here at the bottom. So we have 9b squared minus 225. This one has a little extra number involved, but it is still a perfect square because 9 is a perfect square and b squared is a perfect square and 225, like they're all perfect squares. So we just still follow our same pattern. We have a plus and a minus, and then we take the square root of each one and we put in that the square root of 9b squared is 3b, because 3b times itself would give you back 9b squared. And the square root of 225 is equal to 15. And you can simply use your calculator if you don't have that one memorized. All right, let's look at another one. What if we have 4w squared minus 49? So we notice we got 4w squared and 49. All are perfect squares. So you want to think of the square root of 4 is 2. The square root of w squared is w. And the square root of 49 is 7. And then we put a plus and a minus. And that's it. And then let's check out 16m squared minus 81. So 16 is a perfect square and 81 is a perfect square. Let's just double check that they don't have a greatest common factor, because on any type of factoring, we want to check and make sure that we've taken out a greatest common factor if we can, or else we haven't completely factored it. So no, they don't have anything we could take out, but we could just take their square roots again. So let's take the square root of 16, the square root of m squared. So that'll be 4 for the square root of 16, and m for the square root of m squared. And then the square root of 81 is 9. So then we need a plus and a minus. And that would be it for number 11. So last one, we have 25x squared minus 121. So let's just double check if there's anything we could do for a greatest common factor. And there's not. But you do want to check for the bigger numbers and make sure. So 25x squared minus 121y squared, you just want to still take the square root of both and put a plus and a minus in between those. So we would get 5x is our square root of 25x squared. And then 11y is the square root of 121y squared. And then we need a plus and a minus. All right, so that is it for our difference of squares.